replicate what the brain does. When you look at the Chinese room, it's a very solid argument in that regard. So symbolic AI might be helpful, but alone symbolic AI can't be enough.
Mm-hmm. So the Chinese room, we are going to do it in the next weeks. So it is a story about, we told it also in the introduction, if you can assume, let's say someone can make some operations, but without understanding the operations, if they are at the end intelligent or not. And because someone can have a dictionary and have a text in Chinese and can translate the text from English to Chinese, but this doesn't mean that he can speak Chinese.
One more limitation of AI, I could talk in the behavioral sense. Let's say I came across a picture of Barack Obama. So there is one more politician who is trying to weigh himself on a weighing machine, and then Barack Obama is trying to put his own weight on the weighing machine so that the weight looks bigger. And now the people in the background are laughing. So when we look at such a picture, people smiling faces, Barack Obama doing that, and the person is doing himself, a sense of humor and the whole idea of the picture, what is happening, it comes to our mind. Mm-hmm. But if you give it to AI, it will recognize some faces, some things and all that. So what is the context? It cannot get only from the picture. Mm-hmm. So in that way, the semantic understanding of the text and how things are related, I think it's much more deeper in a human than in simple AI.
Yeah, it is. So probably with logic or with simple logical operation, this cannot be succeeded. Let's revise what we saw last time, because we are going to finish with the logical part today, and we are going to enter a new part, how neural networks are really applied and under which principles govern the application of artificial neural networks. So last time we saw the artificial neural network as conceptualized by McCulloch and Pitch in 1943, and we saw that it was a conception based on logic. They thought that by implementing propositional logic, they could discover how the neurons in our brains work. So what did they say? That neurons build chains, let's say, in our brain and our body and everywhere, and if an impulse comes to them, they may get activated or not. And there is, for example, on the body we have a neuron, a receptor that understands if something touches the skin, if the touch is cold or hot, and there are different receptors for each case, and these receptors send a message to different neurons until it comes a signal in our brain, and we then act, etc. So they made this simple example that they said, okay, if something is cold and you feel it once, it feels hot, but if something is cold and touches your screen for longer time, then you feel really that it is cold. And by having a receptor for cold and hot, and using this propositional logic, these logical operations, they created a network of neurons that could model the cases that you feel cold or you feel hot, depending on the stimulus you felt. Of course, this model of McCulloch and Pitts was a mere simplification, although as we saw, they thought they discovered really how the human brain works. Do you remember what they said? Come on. They said that it will change psychology because now we can measure how humans behave in cycles, they write in their initial paper. Of course, it doesn't happen. There is no such transformation, scientific transformation. But still, this model was applied, was taken, the idea behind it, and it is used today in all state-of-the-art artificial intelligence algorithms, or in many state-of-the-art artificial intelligence algorithms. And we went from the network that they made to this model, the so-called perceptron, that also has neurons, weights, and the threshold, which is activated based on the weights of the connections between the neurons. Do you remember how it functions? Yeah, please.
Like what you said on the previous slide, that there is no real impact on psychology from these kind of experiments. I would say there is some impact, like if you approach, let's say, mental disorders, about 60 to 70 years back, they were mainly dealt in a psychological environment with some social experiments and all those things. But today, if any person is going through any disorder, he is more labeled as a biologically disabled person, because everything is being boiled down to a very specific area which is not correct in your brain. So these kind of methodological approaches have certainly changed the way we see disorders. So yeah, I kind of disagree with your statement.
Yeah, you're right. But of course, it's not like the brain really functions so simply as they assume. We also discussed last time this point, and also you're right. And but we also posed the question: how do you do research? You know it better in neuroscience. You try to find spatio-temporal relations. No, this is also what you say. You gather some small parts of the brain and you locate that there is probably a problem. But we also reflected that probably this is also simplification in a way. I don't know.
Yeah, I'm not talking about the validity of the method. I'm saying it has changed the way we think about the disease.
Yeah.
So it has changed the sociological structure or construct of a mental disease.
Mm-hmm.
That's what I think.
Yeah, you're right. And we also use it until today. So definitely we're here discussing about it. So it changed a lot. So, and we did these truth tables. Who wants to do one again, a truth table, so we make a revision? I'm not doing it. Someone needs to get up, pick up the marker and do it. And wait. Yeah, seriously. Who wants to do it? It's easy. We have a neuron. We have two. We have one neuron here, one neuron here, and one neuron here. We have their connections, and these are input neurons, so they get some values. If this is A and this is B, only the one might be activated, or both, or none. And we want to know what is happening to C. If C has a threshold function, what's a threshold function? It has a threshold, it has a function that this threshold is overcome or not. So we have, do you remember, we have the Heaviside function. I did it wrong, correct me people. What does it say? Do you remember? So, what they send a message, these neurons, and this neuron has a threshold. And if the messages are bigger than the threshold, then this neuron is activated, otherwise it's not activated. These messages, we call them weights in contemporary neural networks. And how, at which value this neuron is activated is in relation to this threshold theta here. So now we want some values, so this neural network can make the logical AND operation. So we need a value for theta, for WA and WB. Come.
1 and 2.
1 and 2.
1, 1.
1, 1.
Can this value be negative?
Yeah, you can do whatever you want.
Oh.
Okay, let's see. So, in this case, how is C? Okay, if only A is 1, is C activated or not? No. This is not the case. If both are 1, then theta, the sum is equal to theta, 2. Then this gets 1, and then it remains 0. Is it clear? Questions? Okay. How would it be, let's say we have the OR function. How should the weight be in this case? Always 1. So if only A is activated and B not, the sum is 1, threshold is 1, and it's just 1. If B is activated and A not, it's the same. When both of them are activated, the sum is 2, the threshold is 1, so C is 1, and when nothing is activated, everything is 0. So, this is the simple structure of a perceptron. We have input neurons, or features as they are called. We have some waves, we sum them, and we have an activation function. This is called, in this case, we use the Heaviside function. Now, this model here is the basis of a lot of all deep learning algorithms. It is applied in a different context with some alteration. We are going to see the generalized version of it. And through it, you can make that Alexa talks to you, that Google talks to you, that the car doesn't crash on the wall, and many other stuff. So, these neural networks and the ones that we're going to do today and the next lecture are part of what is called deep learning. What have you heard about deep learning? Come on, it's on the news. If someone wants to sell you something, they tell you, oh, it's deep learning happening in here.
So it's a subfield of machine learning, and it's especially working with neural networks, and so it's pretty much a structured or a simplified way of the neural system we've been talking about earlier, and yeah. That's it. Yes.
I think the only difference we call it deep is because it has more layers in between than the infinite.
You are cheating. We haven't been there yet. You're right, of course. But I want to hear what the conception is. Let's say you don't know what it is at all. What do you hear in the society that it is? It's magic, usually. They tell you it's a black box, it's something that you cannot see. You're right, it's neural networks with more layers. What does it mean, layers? With more rows of neurons. And that's why it's called deep, actually. And it's called deep because you lose somehow how the algorithm functions and you cannot see what exactly happens there. So you're both right. Deep learning is a subfield of machine learning. What is machine learning?
Making machine learn something?
Making taking a machine learning, exactly, actually, so they wanted to learn at the start, at the field of part of computer science and machine and code, what is it called in English? In mechanical engineering. They wanted to try to make machines that do certain functions or make robots are they intelligent or applications be intelligent. So they started using specific statistical methods that most of them already existed for 100 years. They weren't new methods, but they found a field of application because these machines had a lot of data, and these algorithms could process large data sets, and so they became part of the field of what we know machine learning now. But they are not new. That's also an interesting part. Although machine learning is hyped the last 20 years, okay, some algorithms as random forests were developed really the last 20, 30 years. If we can say that this is also something new, something that was discovered 30 years ago. But for example, other algorithms are 150 years old. They are not new at all, and at this point there was no machine learning taking place. But the digital change in the society made it possible that a lot of data became available, and some older methods became really useful suddenly. The same thing is with neural networks. Neural networks were they discovered, not the McCulloch and Pitts version, but the version that is used today, weren't used at all, or very little, because they had some limits, as we saw, that, okay, you make the model, you may make it complex structure, but if you don't have enough data to train it, you cannot make good inferences with it. So they stopped using them, and there weren't many people doing research on neural networks. But suddenly, because of this data boom through the internet, all these methods became really important again. And as the field of machine learning was developed, also a new paradigm of thought was developed. As we saw that these people 100 years ago, they thought that through logic that they can understand how the human think, that through logic they can create machines that think. In this way, there is another different way of thought that says that given a lot of data and specific procedures, now you can make machines intelligent. But what is machine learning actually? It's really interesting because it violates, more or less, all of the epistemological assumptions made about how correct science should be done. Because why? You know, in traditional science, usually you have a theory, you make an observation, okay? So, given the theory, you make an observation, and based on the observation, you decide if your theory is true or not. Arrow turns blue. If I have this theory and suddenly see a chair that is black, my theory is rejected, and they have to correct it. So it's the same with experiments. We have a theory, we make experiments, we get a result. We have a theory, we make statistical research, we do empirical research, we decide if our theory is correct or not. This is a simplified version of the scientific method in the 20th century. But machine learning doesn't do that. Machine learning usually doesn't take into consideration what happens in theory. So what does it do? It only tries to represent, to find relations between data, between inputs and outputs. So you put some data inside, You put some data as a result, and you let the model train itself. And then you evaluate if it can predict well or not. And that's it. But the interesting part of it is that if you have made also, and this is also a problem in statistics usually, that given the theories you can correct it or not, because it's also an issue there, is that you can make models, data models, that tell you nonsense. They might predict something well on the data you put in them, but they actually have no descriptive value about the world. And this is why this comic is funny. So we have our linear algebra that we talked about before. We put our data and we get an answers. And what if the answers are really, really stupid? I change a little bit the algorithms, and if they start looking good, I'd say I created a great model. Also food for thought. And also, you must think about it every time somebody tells you, my statistical model gives the truth. Look what my statistical model says, this is it. You must also make this relative thought between theory, between the data that someone uses, and the descriptive power of the method. This is not so much connected on artificial intelligence, because artificial intelligence systems using neural networks are not concerned to make usually predictions. They try they do predictions, but the cases are very, very, very limited. For example, you have a neural network that, for example, in the Google thing we had at the first lecture, that takes a word, a signal, the voice of us, and translates it to a word. And this is the prediction that actually it makes. But if you have a machine learning model that predicts the unemployment rate of a country, then it's really important to think of the limitations this machine learning algorithm may have, or the statistical model has, the econometric model, etc., etc. So we have this paradigm change in thought. Which says we have an input, let's say our input is A, we have our output, B, this is what we want to get, and we have our X, which are our unknown values, and we train a model, and we find the best values for X, so that that a function of A and X can give us B in a simplified way. So these algorithms, also in artificial intelligence, also in machine learning, also in statistics, they try to find relations between features, between data, between numbers, actually, because we translate everything to a number and we give it to the machine. These relations may be qualitative or quantitative. We can say that a sensor can understand that the temperature, for example, has got higher, or it can say it got higher by 3 degrees. Or the sensor can understand this is blue and this is red, or it can say this is an RGB value 211. There are 2 ways we do that. The quantitative relations, we find them through regression. The qualitative relations, we find them through classification. These are the 2 types of machine learning algorithms that they exist. And we represent it as a system of linear equations always. So we have A, we have B, and we want to find this X so we can map A to B. Or we can find the relationship between A and B. And although you can imagine that we have a lot of equations, complex mathematical systems, So to find these values, we cannot solve it analytically. It's too complicated. Even in this case, I didn't see any one of you solving it with equations. You actually came up with a solution doing math, trial and error math on your head. So in complex systems, this trial and error is used by optimizing a cost function or a loss function. What is a loss function? For example, we want to say that we know that the true answer is 1, 1, 1, 0, for example. So we make random values of these. Let's say this is 1.5, this is 3, and this is 0.1. Okay? Given our inputs, we calculate an output, a C predicted. It could be like 0.3. Do it nice, in a nicer way so it becomes clear. Excuse me for being. Okay? So, what value did I give to theta? 0.1. Okay. We have C predicted here. And this C predicted could be 0.4, 0.8, 8.7, and 4. Okay? Is this what we want as an answer? No, so we apply a loss function. What, for example, it could be the sum square of errors. So we make 1 minus 0.4 for this point. So how much does our prediction deviate from the actual value we want to get? Plus 0.1 minus 0.8 in squared plus 1 minus 1.7 squared plus 0 minus 4 squared. Okay? So we get a loss value. And we want to minimize this loss. If we have perfect values, 1, 1, 1, 0, how much is the loss? 0, exactly. The loss is 0. Now, usually in mathematics, we know how to minimize a function. How do we minimize a function in mathematics? We take the derivative and we make it equal to 0. And we find the minimum in this way. But usually the equations are so complicated we cannot do it. So what do we want? We need to find the minimum of the equation. If we plot here L, let's say this L, and it's like that. And we want this point. We do it iteratively. So we calculate the random values of L. We calculate the gradient, because what does the gradient give of a function? It gives the tangent. So what do we know through the tangent? We know to which direction we should go, so we can go lower. So given the actual value and its gradient, we can make steps iteratively. Get a new value, retrain the model, get a new loss. Calculate its gradient and move. And we can reach the minimum. In this way, we optimize the cost function and we find the values, our weights and our threshold, or these x values in complicated models. Questions until now? Okay. So let's get more complicated now. What do we have here? What has changed? What did you see that wasn't the same as before?
A kind of feedback loop.
Feedback loop. Okay, we have this error thing here. What else? The activation function. What else? We have more new stuff. We have a unit step function. Before it was the same. We have here more features as before. In our case, we only have 2. And we have also this, which is no x. What is this? This is called the bias term. Or who have you, of all of you, have done simple linear regression in a course in statistics? What do we have always beside our input values?
Plus C.
See the intercept, exactly. So we have an extra value always. The same happens in machine learning. We call it a bias term because we make it for mathematical reasons. For example, if all this is symmetric, the right model cannot get optimized because we get the same values again, and my whole model changes to the same direction if I try to optimize it. So by having a bias, for example, I'm breaking the symmetry. That is one of the reasons that we use bias. So again, we sum the inputs as we did before. We sum 3 plus 0.5, but now we don't have the Heaviside function. We can have whatever function we want. Because why? Because in machine learning we have a problem to solve. We want to find the best way to represent B through A and X. This activation function, for example, we are going to learn the sigmoid function next. That is going to be used. What is this loop we have? We can, for example, if in our simple neuron model, we would sum it up, we would have our activation function, it would be the Heaviside function, and we would get a value. And we would apply our cost function, get the error, and given the error, we could find the new input and do the loop again. So what we do always in machine learning, in neural networks, is we start randomly with some input values, calculate the value of our function. Given the loss function, we find the error, and given that error, we change our starting value until we minimize the error. Okay. If we have classification, what is classification?
Resides not like a regression continuous.
Exactly, like our dependent variable, the quantity or quality we want to describe is discrete. For example, I have this data here, which are the people in Titanic, some of the people who died in Titanic. So we want to see what kind of characteristics do the people who survived have. So I have here my data table. I have a value that's called survived, and it is with 0 and 1. Survived is notated with 1, or died with 0, because we need to represent everything in numbers. We have what kind of class they traveled, first class, third class, etc. We have their name, we have their sex, if they're male or female, and we have their age. So, if my output is, if I want to predict if they survived or not, I need to transform everything that I have here to 0 or 1. And this I do it with the Heaviside function, for example. But if I have, for example, I would have survived, died, or I don't know, but that's okay. So if I wanted to see at which predict what class they traveled, given that if they survived their sex and their age, I couldn't do it. Why? Because I don't have 0 and 1, I have 1, 2, and 3. So this function doesn't fit. So I would need to find another function to do it. Is it clear? We will see how we do it. But I want you to conceptualize that these are not fixed. Depending on your problem, you can change it. Okay, the most typical function used is not the Heaviside function, it is the sigmoid function, which is like that. It also has values from 0 to 1, but it is not 0 and 1 as before. But why, what it can take, for example, if my value is here, it could be 0.9, or here it could be 0.2. What advantage does this function give to us?
Well, you could slowly approximate 1 and 0, not just discrete.
Exactly, and thus we can estimate the probability that something is or is not. I can have a value 0.7, I can predict with 0.7% certainty based on my model that Browns died, for example. And this function is given by this equation, the sigmoid function. And it also has some many other advantages, like it has a simple integral, because the exponent as a function is really, has many benefits mathematically, because it has the same derivative. The derivative of exponent is exponent. So instead of using Heaviside function, I can put the sigmoid function here, and at this point optimize my loss. And then, of course, at the end, if I want to make predictions, I could use the Heaviside function and say, okay, if something was with, I got a result of 0.7% probability, I can reduce it to survive, to, for example. Okay, this is a generalization of the perceptron, also called logistic regression. And this is actually something that happens all the time, this process in a neural network. So actually, at every connection of a neural network, here, I make the same process. What's that? Okay, let's see. This is a feed-forward neural network. We have our inputs, as before, our outputs, as before, but now we have more layers here, more neurons. They are called hidden layers. Why are they called hidden layers? Because you don't see them from here. I'm joking. Because if they are in the middle, then you cannot actually see their values directly, what values they get. And this is the standard definition of deep learning, is that something that has more than one hidden layer is a deep learning algorithm. This is one definition. Others say that you must have more complex connections here. We're going to come to it. So here we have again our weights that go to each of the neurons in this case. And we do the same thing. We give some random values, we calculate the weights. Here we have a function that takes all the inputs, the weight of this with the value of this, the weight of this with the value of this, the weight of this with the value of this, sums them up. Here it has a function, and it produces a new value. And then based on these weights, this new value is sent to the next layer of neurons. And each of these neurons get the value of the weight with the value of the neuron, the value of the weight with the value of the neuron, etc., etc. Sums them up. Given activation function, it transforms this sum to a new value. And it sends it here, and here, etc. And again, we come here, we come to a result, and we want to see if our predicted value is equal to the actual value. We have a loss function, we make the difference, and we optimize. We make new values here, and until we get the minimum loss. And this is the best prediction we can make. So if we take one neuron, this is one huge neuron here, we have again, it is the same model as before. We have our inputs, which are the weights in this case. The transfer function, which is actually the sum of what comes inside. the activation function, it is a function, the Heaviside function, the sigmoid function, the function that we want to do. And we send these activation values further. What do we don't have to do that we saw before?
The error.
The error, exactly. The error comes only at the end, at the output. So this, you can also get the activation value A by this equation mathematically. W are the weights, A are the values that had the previous neurons. So we multiply them, because what does the matrix multiplication denote? It's the sum of the combinations for its observation. Because if I have a vector A1, B1, and the vector here A2, B2, what is the multiplication of it? What's the result? Come on, people.
A1 times A2 plus B2 times B1.
Exactly. So it's the sum. But we can do all the sums together by simply multiplying the matrices where we have our data inside. What also do we have here? What is this B?
Yes.
The bias. We always put a bias. Always. Each time we put it. Okay. So let's now again see how we calculate the stuff. We assign randomly weights to our network. We have our inputs and our outputs. We have a loss function that we decided before which one to use in respect to the nature of our data. You use a different, for example, if I did classification and I only had 0 and 1 values, I wouldn't use this loss function. I would use this loss function in regression. In classification, I would need a function that says, okay, did I classify it correctly? If yes, I don't get a penalty. If not, I get a penalty. I have the training data. For example, I would have in our example 3 features. If I wanted to predict if someone survived, I would have the class they traveled, their sex, their age, and I would have observations. Each row here is an observation. What does it mean? It's each case, each passenger's characteristics. And the learning rate. What's a learning rate? I decide how much I let my network learn. How much do I take into consideration the loss I calculate? The reason that I do it are mathematical, actually, why I import the learning rate, so that I can find the optimum minimum in our loss function. We aren't going to get to it more. I'm just going to explain it to you qualitatively. If I make a too big, for example, if I calculate the loss and its derivative, the derivative value might be too big. And if it's too big, I won't get here or here, I might get here. Because I tell it, the algorithm, the result tells me that I should move a very huge step. And if I move a very huge step to the left, the value is bigger than before. So I am not calculating the minimum, but I am diverging from the value I wanted. So we import a learning rate that makes this derivative smaller so that I can come to the required minimum. Just qualitatively for you to understand it. So, okay, I have the neural network. Questions until now. So, we have the inputs, we assign random weights, and we calculate the output. Here it says features and labels. Features are called what I explained to you before. the class of the passenger, sex and age, are the data that we put as input to our model, our body features. Labels are called in classification the values our variable output variable can get. We would have a label for what, for survived, and the label for died in our case. So, given our features, we have our features and labels. Here says get a random mini batch. What is the mini batch? So, again, qualitatively, instead of taking all the data that I have to train a model, at each iteration, I only get a part of the data and put it in the model. This is called mini batch. Do you know why? Probably I would do it. I do it. Why I don't take all the data and take only part?
To test it later.
Sorry?
To do testing afterwards.
Good thought, but we do it that at the end. That's true, we do it. But this is not the reason why we do it.
When you don't want the completion of the whole data before we update the weights. By using a mini batch, we are actually using a subset of data to update the weights, which is much faster than taking the data of the whole set and then updating the weights.
This is also true, but this is not the main reason. You do it, actually it becomes slower if you use mini batch. Why? Because if you take all the data, your algorithm more or less finds one specific pattern in the data, which is the mean. For example, we get the mean of all the data. But what if I get pieces of all our data? Each of them will have a different mean. Is it? Look, it's logical. So, if I want to train a function, it takes consideration more abnormalities, more anomalies that exist in the data, so it can find a better minimum for a simplified qualitative explanation of it. And for this reason, it actually takes more time, because imagine that given this data, this cost function changes shape each time. So by changing shape, it gets more time to find actually global minimum. So given the inputs and the weights returned here, and having selected some data, I get an output. I have the loss function, and I calculate the loss. L predicted minus actual. Okay? And then, what do we want? We calculate the derivative. Yeah, please.
I think in that case, if the data is, if the whole population data is kind of a repetition of small samples, then it's much easier to go for mini batch, because then let's say I have 1,000 samples, I have a batch of 100 each. If the whole sample is just a repetition of some data, then I just use 3 or 4 batches and my whole thing has converged. But at the same time, if my population does not have much repetition, then we need to go more in terms of number of batches to be used. But in case of like very repetitive data, the number of batches thing can be very efficient, because you don't need to do the computation of loss across all samples, but just a subset of it, because everything is converged.
It's efficiently, but it takes more time. It really takes more time. It's more efficient, but it takes more time.
In which step would it take time?
Sorry?
In which step would it take time?
You need more steps. It's probably quicker to make the calculation, but it makes more steps to convert. You find a better solution. Probably the calculation of each step is faster because you put less data, but you need more steps to convert, because the loss function changes all the time. And for example, it would go like that. If I do gradient, I don't take mini batch, I could go like that, and if I get do mini batch, it would go like that. I can show you an example after the course. So, why do I need the derivative of the loss function? What does the derivative give us? We said.
Shows us in which direction the function passes.
Exactly. Exactly. So we can see also how our loss function changes. So we can see if I get an error here and I take the gradient, I can see how much it changed given the specific mathematical operation at each point. Complicated, but you will see what I mean. So, for example, okay, I calculate the gradient, I see how the loss function should change, and I want to be a smaller error. What you said? You said, sorry. You get a smaller error, so I know to which direction should the weight change, so I change my weight given the learning rate that I chose in the beginning and the direction that our function says it should change. And I calculate new weights. And given the new weights, I do the same operation, calculate the loss, its derivative, and calculate new weights until I minimize the loss function. But this is now the difficult part. How do I calculate how much the weight should this weight change? Because the difference I calculated, the loss function is here. So these are two completely different things. Okay? So what do I have to do? Actually, what I did when I computed these results is I started from here. I took the values and came here. I activated the values through the activation function. I sent the values with the weights here, here, here. I got a prediction, and from the prediction I got the loss. And I have now the loss here. So what do I need to do? I have the derivative, and I know how much it should change. So I need to retransform this derivative in a way that this understands. So I need to pass the derivative from here to here, from here to here, from here to here, from here to here. And for do that, I need to take the loss function and make the derivatives in respect to this neuron, to this neuron, to this activation function, to this input function, to this weight, to this activation function, to this sum that we calculate here, then to this weight. And in this way, I can calculate how much did the loss function here change in respect to this weight. And then I can subtract the value. Is it clear? Should I explain it again? It's really important. I have a loss function, but I want to change to see how the loss function changes in respect to this weight. So I get the derivative of this loss function in respect to this weight. If this was weight A, I would do the derivative of the loss function to weight A. And to calculate this value, as we see, as we are going to see, we need all the derivatives from here to here. So I will calculate the derivative here after the activation function was activated. Then the derivative before the activation function was activated, which is, at this point I have the sum of these weights. Then I'm going to calculate the derivative of the weight, of this weight in respect to the loss function, then of this activation function in respect to the loss function. I will do step by step. I will come here to change the value of this weight. This loop from when I calculate the output, this is called forward propagation. When I start from here and go back, this is called back propagation.
But are there a lot of different ways to reach this very, very last loss function between the input and the first hit layer, or the node of the first hit layer that the very point we had, for example, that we just heard now. So wouldn't we need to calculate this back propagation for every single way to reach this loss function.
Yeah, we do it. Actually, because this point, for example, this way, is connected always to all these and this no error, because it is here. So we calculate all this here. So these no errors, and the connections that go to this no error is what we need to calculate this.
So now if we do this for every single year in our systems, then just 100 years.
This is why we use linear algebra. In linear algebra, you can do these operations in one. You don't have to repeat its process. You will see when we compute it, that there's one calculation this time actually. In one matrix of calculation. With all these simple changes are included. So, okay. Let's say I have this neural network. Okay? Here are my inputs, and they have 3 outputs. What is interesting in neural networks that isn't like that in regression, for example, is that I can put as many outputs as I want. So I could have modeled that I give types of apples as input, and it can give me 3 outputs. For example, its color, its shape, and if it is, how old it is, on the same model. This couldn't be done in a simple regression or in any single statistical model. So in this case, I have this loss function. What does this loss function say?
I mean, it's the difference between the ideal output and the output which this model is giving.
Exactly, in square root. So in this case, it would be y1 minus y1 actual, so y1 predicted minus y1 actual. y2 minus y2 actual, y3 minus y3 actual. Okay.
But doesn't this assume that we know some kind of optimal way of, some kind of optimal solution?
That's the trick with machine learning. We already know the solutions. And this is what we discussed the last time with open-ended intelligence. That it could be, is this really intelligent if we know already what we want to know and just we find a way to describe it. While in open-ended intelligence, we saw in the presentation last time, we thought, could it be a real artificial intelligence if the robots or the algorithms don't know the result, they find a result somehow. So what else do I have here? I have these zetas and these sigmas. The zetas are the sums. For example, zeta 1 is the sum of w1 multiplied by a1 plus a2 multiplied by this way plus a3 multiplied with this way plus a4 multiplied by this way. This is plus or by. This is given by this equation. Okay? And then, getting these sums, these zetas, I put these sums in our activation functions. And this is how I get y in this case. Y hat is equal to the sigma function, the sigmoid. When you see this sigma, usually it's the sigmoid function. Given the zetas that I have calculated from the weights in the input feature. Okay? So, if I want to calculate this weight, we said we need all the derivatives until here. The first derivative I can calculate is the derivative of the cost function in respect to the variable y, which is our result. If I do the mathematics, which is, so we need the derivative of this equation in respect for y1, for y2, y3. So if I, which is the, if I have this function, what is the derivative in respect to y1 of this function?
Or y1.
It is this one. What is the derivative in respect to y1 hat? It's also the predicted values. So,
I'm sorry.
I just integrate. Is this a function of y1? No, it goes away. Is exactly. This also goes away. So I have only this to calculate the derivative. It is 2 minus y1 minus y1. Simple mathematics. High school. We did it in high school. Okay. So if because I want it for all y's, I make this generalized form. So I want for it the change for its predicted value j, yj. I have this equation that's also here. Is it clear until now? More mathematics. So I came here, I calculate this derivative. Now I have my sigmoid function.